Uh, Good afternoon and welcome again to my YouTube channel, Pearson at Excel International Maths by Mr. Kamotho. And we have been looking at the syllabus of Pure Mathematics 3, and we are in chapter 5. And I would want us to look at page 108. Whereby we are going to understand something to do with natural logarithms. And under this one, we are going to look at some explanation on page 108, and we're going to understand that the graph of y is equals to natural logarithm of x, or rather ln x as it's popularly known, is a reflection of the graph of y is equals to e raised to power x in the mirror line, or along the mirror line y is equals to x. And we have been knowing that the graph of e raised to power x is simply like that. This is the graph of y is equals to e raised to power x. And if we talk of this one as the mirror line y is equals to x, then you realize that the graph of ln y is equals to ln x is a reflection of the graph of y is equals to e raised to power x along the mirror line y is equals to x. You can see several features there, that the graph of ln x passes through 1, 0. This one is a reflection of 0, 1, where the graph of y is equals to ex passes. It does not cross the y-axis, or rather the y-axis is an asymptote. This means that ln is defined only for positive values of x. You can already see ln is defined only for positive values of x. In other words, we do not have natural logarithm of negative numbers as verified by this graph. This means that ln is defined only for the positive values of x, and just like we've said, we don't have the natural logarithm of negative numbers. And you can also see that as x increases, ln grows without limit. But of course, as x increases, you can see ln grows without limit, and of course at a slow rate. As opposed to ex. You can also use the fact that logarithms are inverses of exponential, because if this one is an inverse function of this, of course supported by the fact that it is a reflection along the line y is equals to x. And we have learned in earlier videos that the graph of an inverse function is a reflection of the original function along the mirror line y is equals to x. And since this is behaving exactly that way, then the graph of the natural logarithm is an inverse of the exponential function. So we are being advised that we can also use the fact that logarithms are the inverses of exponential functions to solve equations involving powers and logarithms. But one basic thing that we must remember is that the ln x is in the expanded version known to be the log into base e of x. This is just what we want everybody to remember, that ln x is the log into base e of x. And having said that, e raised to power ln x is equals to the ln of e raised to power x which is basically x. We are going to find that in example 5. And in example 5, we are talking about, let's just solve or respond to example 5 here so that we can see what is expected of us. We are told that to solve the equations giving your answer in exact form. And the equation is e raised to power x is equals to 5. And of course, if we introduce natural logarithm on both sides, we are going to say ln e raised to power x is equals to ln 5. And having said that, it is true that x is going to be ln 5. X is going to be ln 5. If you look at this, if you look at it this way, you will find that x is ln 5. But I want to introduce something very familiar in this particular setup, which will work exactly like this, or which will support something like this. We have been following the log into base 10, which is the normal logarithm, and we say the log to base 10 probably of 100, we all know it is equals to 2. And this one is written in logarithmic notation. This logarithmic notation, if we move the anticlockwise movement, if we move anticlockwise, then it sends us, or it gives us, the index notation. This is logarithmic notation, and let us talk about the index notation here. And the index notation is that 10 raised to power 2 is equals to 100. And this is what I'm just calling the anticlockwise movement, which is 10 raised to power 2 will give you 100. And at the same time, our part A is exactly in this format, which talks of, if you again talk about the anticlockwise movement, you will get back here and we say log to base 10 over 100 is 2. So if we have e raised to power x, which is equals to 5, anticlockwise, we are going to say log to base e of 5 is equals to x. But what is log to base e? Log to base e is simply ln x. Log to base e is simply ln x. You can see here, log to base e is simply ln. And this log to base e, then we are going to simply say natural logarithm of 5 is easily x. That is the solution of part A in that particular question. Let us talk about part B. Part B says ln x is equals to 3. And now that we've just learned ln is log to base e, let us just introduce it and have log to base e of x is equals to 3. If we use the anticlockwise movement, then we are going to say e raised to power 3 is simply equals to x. And that is it. As far as part B is concerned, it is very important that we note that the log to base e obeys the same rules and the same steps as log into base 10 or log into any base. What we have introduced here, log to base 10 over 100 is 2. We know that 10 squared is 100, and this one gives us index notation. So the same thing, log to base x being equals to 3, and ln x being equals to log to base e of x, which is equals to 3. With anticlockwise movement, that means e raised to power 3 is obviously x, and that is exactly what we have found out to be. Yes, that's the end of example 5 and the introduction of natural logarithm. Moving forward, we shall catch up with other other relationship which include log to base e. Yes, visit my video as frequent as possible, subscribe and share so that we can work together. All right.